Hi, everybody. Thank you for joining us today for SPS's Fall Virtual Colloquium Series. Today we have Dr. Daniel Russell with us from Penn State University, and he'll be giving a talk titled The Acoustics of Ping-Pong. Whenever you're ready, feel free to get started.
Okay, so thank you very much for this invitation. It's kind of a fun thing. I thought what I'd do before I jump into the ping pong acoustics part is I would give you a little bit of an introduction to who I am and my involvement with physics. And since this is an SPS sponsored activity, I'll just describe my background in SPS as well, and then talk a little bit about what acoustics is, because it's a field that not a lot of physics majors are aware of the fact that there is a career path in acoustics that is a lot of fun, that I want to highlight. So let's see if I can make my slide advance. So I started out as an undergraduate as a piano performance major. Piano performance and French horn were my two instruments. Piano performance was my first instrument. I started as a freshman piano performance major, very quickly realized that I was not talented enough to be able to make piano playing a career path that would actually make a living. I was not good enough to be a concert pianist. I liked playing a lot, but I didn't want to do the jazz club circuit kind of thing, and I did not want to teach piano lessons my entire life. So I had an interest in science and math as well, and so my sophomore year I added a physics degree, so I ended up graduating with both a bachelor's degree in piano performance and a bachelor's in physics. And then my senior year, my advisor had me do a project on the physics of pianos, and this light bulb went off in my head saying I could do physics and music together. So I went to Northern Illinois University and studied with a guy named Tom Rossing and did an applied physics master's degree and studied the physics of musical instruments. Specifically, I was looking at the nonlinear behavior of piano hammers. So I got to do the physics of piano hammers for my master's thesis and had a lot of fun learning how to do physics. It was at that time period I also realized that I really wanted to teach at the college level. I had a chance to teach undergraduate labs and enjoyed it a lot. So I got to do that. I guess I forgot to mention when I was at Bradley University, I was also involved as my undergraduate. That's where I started getting involved with the Society of Physics Students and Sigma Pi Sigma, the Honor Society. After my master's degree, I went to Penn State to get a PhD in acoustics. I discovered that acoustics and sound and vibration was the thing that I really wanted to do with my life. And so I did a structural acoustics and vibration PhD work. I had to do with something called a fuzzy structure. I was doing some modeling of devices that we would commonly call submarines, but I was not allowed to call them a submarine because my funding came from the Navy, so I was allowed to call it a cylindrical object with hemispherical end caps that was submerged in a compressible fluid. I couldn't call it a submarine, but basically the idea was we wanted to know how sound waves would bounce off of an object that had lots and lots of complexity on the inside, but we didn't know anything about the details. So our knowledge of the internal structure was fuzzy. And so we did some modeling of mass spring systems and some complicated math and physics, and had some fun looking at ways that structural objects vibrate. After getting my degree, I ended up at Kettering University. I don't know if we've got any Kettering University students. I know that the advisor there was going to try to share the link with them in their Society of Physics groups. I spent 16 years as an undergraduate physics professor. At Kettering University is a co-op school, so they have two groups of students that alternate between going to classes and then going to a job. They have an applied physics degree, an engineering physics degree with a minor in acoustics. While I was there, I developed an acoustics laboratory, got an acoustics minor going. I was the initial advisor for the SPS chapters that started at Kettering and Sigma Pi Sigma, and those chapters, they have two chapters for the two groups of students, and they're very strong. I think recently they've won a couple of awards, the National SPS Awards, so that was a lot of fun. 16 years of teaching undergraduate physics that I really enjoyed. But then I got enticed back to return to Penn State, where I've been for the last 9 years. And Penn State has a graduate program in acoustics. And that's a little special because we are the only program in the entire United States that offers a PhD in acoustics, the study of sound and vibration. There are lots of other places where students can go to study acoustics, but those places all have degrees in physics or mechanical engineering or electrical engineering or some other kind of an engineering structure. Penn State's the only school that offers a PhD specifically in acoustics. We've got like close to 1,800 students that have gone through our program in the last 50 some years. 230 almost are PhDs. So chances are very high that if you ever run into someone who has a PhD in acoustics, probably a pretty good chance that they got their PhD from our program. So that picture right there is me standing next to Whitney Coyle, who is a physics professor now at Rollins College in Florida. She does some really neat work with clarinets and teaches undergraduate physics to students down in Florida at Rollins College. I wanted to say just a few things about our program, not so much to advertise Penn State's acoustics program, although that is something I'm interested in doing, but I want to make sure that undergraduate students that are watching this, especially if you're an undergraduate physics major, I want you to know that acoustics is a viable career path. A lot of times acoustics gets left out of physics areas. You learn about waves and vibration in your introductory physics class, and then that kind of gets tossed off as something that's really not worth looking at for the rest of your life, and we do all kinds of high energy nuclear particle physics kind of stuff. But there are a lot of really fascinating things that we can do with sound and vibration. In fact, of the students that come into our program, we usually have about 15 students in our master's and PhD programs coming in every year, and roughly a third of those have backgrounds as physics majors. The others are engineering majors, some math, some acoustics, a few. There's only 2 schools that I know of that have an acoustics undergraduate program. So most of our students come from a physics and engineering background. And a lot of them have some kind of a physics and engineering background along with an interest in music, which is similar to my background. So the pictures on this page show some students that are taking measurements, noise measurements of an aircraft flyby, local aircraft, a local airport not too far from here. The professor takes the students out to the class. They make measurements, but more importantly, they're learning how to analyze the data, how to take and extract signals from the data they're collecting as part of a data signal analysis class. One of the things that makes acoustics interesting to me is that there are so many things you can do. So in our program, for example, what makes it special as an acoustics program is the fact that we have about 20 courses just in acoustics. Some fundamental acoustic and vibration, signal analysis, some experimental techniques, but then there's all kinds of extra topics like computational modeling in acoustics and nonlinear acoustics and ocean acoustics and spatial sound and 3D. So how do you design systems to do spatial hearing, 3-dimensional hearing, binaural sound or surround sound systems, psychoacoustics and sound quality, acoustics and musical instruments, architectural acoustics. We have several courses that are even on this list, like biomedical ultrasound, things in metamaterials and noise control and vibration, aeroacoustic modeling. Our faculty do all kinds of stuff. This is just a list of some of the areas in acoustics that faculty at Penn State do, but these are all career path options. Looking at like active control of sound and vibration. Aeroacoustics has to do with the noise. There's a lot of people that study noise from aircraft, looking at designing concert halls, looking at the way that sound travels through the atmosphere. Biomedical ultrasound is huge right now, using sound waves to detect cancer, to kill cancer cells, to deliver drugs where they need to be in the body and then distribute those drugs where they need to be. Electroacoustic transducers, designing headphones, designing microphones, designing loudspeakers. The home audio system right now is a huge market for both for the consumer audio, both in terms of employment and in terms of designing equipment. We have people that do noise control. We've got people that do outdoor acoustics for the way that sound propagates outdoors, above ground, and under the water. In fact, there's a lot of climate control measurements right now. One of the best ways of measuring the effects of climate change are to measure the temperature of the ocean, and the easiest way to measure the temperature in the ocean is to measure the speed of sound in the ocean. We've got people that do psychological acoustics, speech and hearing. People that do looking at hearing aids, at hearing health problems, at hearing concerns, and trying to understand speech, both from the sense of even a computational and machine learning perspective, trying to allow computers to interpret speech, but also having computers to produce speech are some really fun things. People that do work with sonic booms. In the U.S., we're looking at trying to get some supersonic transports. You can take an aircraft from New York to L.A. in about an hour and a half, 2 hours, instead of the current flight path. But that requires sonic boom propagation over ground, and there's people that are trying to design the aircraft, and then people that are actually analyzing and measuring how the sonic boom travels through the atmosphere to try and correct it. Ultrasonic imaging, structural health monitoring, using acoustics to detect flaws in structures before they start to degrade to the point that they need to be repaired. Ultrasonic imaging using sound waves to see inside the human body. A lot of really cool stuff. So the field of acoustics, I guess one thing I could just impress upon those watching is that acoustics is not just loudspeakers and concert halls. Acoustics is a huge variety of things that have to do with sound and vibration. In fact, you cannot go through a single day without engaging with acoustics in multitudes of ways, from medical applications to audio applications to the things that you hear and see, noise in medical applications, all kinds of things. So it's a career path that is available and viable for physics majors. I just want to toss it out there. Penn State's not the only program you can go to study it. It's a very good one. We focus exclusively on acoustics, but I just want to toss it out as a career path possibility for students. Job markets. These are some places that our students go. We have about 18 students at Bose. I've got about 15 or 20 students at Apple. Apple, I think, employs 200 engineers doing things with sound and vibration, both from laptop computers to hardware to desktop computers to the mobile devices you hold in your hands to the headphones and loudspeaker systems. We've got people at most of the national laboratories doing some really interesting things with physical acoustics. There's a group at Los Alamos and Argonne National Labs that do things with thermoacoustics, acoustic refrigeration, using sound waves to refrigerate, to move heat back and forth in a way that's approaching the efficiency of the Carnot engine cycle. It's got some really neat applications. Active noise control is a big issue in a lot of both vehicles for like automotives and airplanes as well. So it's a huge place, and not even listed on this page right now are probably the hundreds and hundreds of smaller consulting firms that do things like trying to mitigate noise problems in schools, in factories, in industry offices, in homes and hotels, trying to make the world a better place to live. To get rid of noise. There's people who do work with national parks. Right now, with COVID happening, national parks are enjoying quiet, and the wildlife in the parks is enjoying quiet like we haven't experienced for a long time, because all of the human noise tends to interfere with things. But there's lots and lots and lots and lots of things that you could do in an acoustics related field. So I want to toss it out as a viable career path that is extremely rewarding and a lot of fun. So if you've got questions about that, please contact me. The Acoustical Society of America is a wonderful organization that has thousands of people that do research and work in industry in all kinds of different areas in acoustics. Toss that out as a career option. All right, the main topic for today is the acoustics of ping-pong. Kind of a really fun topic that I did a couple years ago. The technical title would be the Vibroacoustic analysis of table tennis rackets. Acoustics of ping-pong is a little more fun. So here's ping-pong paddles are kind of cool. So I'll show a video clip here, and I'll show a video clip because I don't think I can reproduce this in my office really well. But a ping-pong paddle is an object that is really convenient for demonstrating a physics phenomenon that you might encounter in a mechanical, classical mechanics or theoretical mechanics course called the Tennis-Racket Theorem. And I realized that I spelled the word principle wrong here, and I already have the video out there, and it's gotten too many views for me to change it. But let me show this video. It's a slow motion showing how when you take an object like a ping pong paddle and you rotate it about its axis, there is one axis where the object is incredibly stable, and it will oscillate or rotate about that axis stably, and it will stay, the orientation of that axis will stay the same while the object rotates. So you take a ping pong paddle, toss it up in the air, it'll stably rotate and come back. There's another axis about which you can rotate the object, and it will also be stable around that third axis. It will rotate about that axis stably so that the axis of rotation never changes. The system just rotates, and you can toss it or rotate it and catch it. That works really well also. But the third one in between those two is an axis for which the moment of inertia falls between those two axes. And if you take an object in this third one and flip it, it almost always twists while it's rotating. So that paddle started with right now, it's starting with the red side up. And as you flip it up in the air, instead of landing one complete rotation with the red side up again, it twists about one of its other axes so that the black side comes up when it lands back down. So this is an unstable rotation. Gymnasts will take advantage of this as they flip and twist to allow themselves to rotate and go through all kinds of gyrated motions when they go. There's one where the racket is twisting several times while it's flipping. But it's just the nature of the inertia. So a tennis racket and a ping pong paddle is a convenient tool for demonstrating that. Another cool thing you can do with tennis rackets is some other simple physics. So we'll get to the acoustics in a minute. This is a paper I found in the physics teacher back in 1994. Really neat story. This physics professor, the physics department got a ping pong table in their lounge area, and so the students and the teachers, the students and the professors were all playing physics at the lunchtime. And this professor, Chris Graney, was new to the game and had never played ping pong before they got the table in their apartment, and he just got clobbered, got beat. Every time he tried to play his students, the students would just beat him. And he decided he would use physics to try and figure out how to design a ping pong paddle that would allow him to win the game. So he did the simple analysis, and this is something that you'll maybe encounter in a theoretical mechanics type course. It's just the conservation of linear and angular momentum when a spinning ball hits a surface like the paddle. When the ball comes in with a spin and hits the paddle, the conservation of angular and linear momentum when it comes off will determine the direction of the spin after the impact. And so he did the math and the physics and realized that most people, when you play and you use a paddle that has rubber padding on it, you can generate spin by the way that you hit the ball, and you can make the ball spin, and when it hits the table it will bounce and come off the table in a certain direction, and depending on how much spin and what direction the spin is, it can be very hard to hit the ball when it's coming back at you. Well, what he did was he took a paddle and removed all the padding rubber off it and smoothed it down and got it as slippery as possible so it was nearly frictionless. And instead of worrying about trying to generate spin, all he did was simply just try to pat the ball back over the other side. All he had to do was make contact with the ball and kind of direct it back. But what happened is, because he had such a frictionless surface, when the ball hit the paddle, instead of changing the direction of spin, which normally happens, his paddle would just let the ball bounce off, retaining the same spin, but that meant it was completely the opposite of what the players on the other side were expecting, and so he started winning games, not because he was a talented player, just because he was a physicist and was able to define a very slippery ping pong paddle that did not change the spin, but it was completely the opposite of what all the other players were expecting when they would play. So that's kind of a fun way. You want to beat your opponents and you don't have the time to learn the skill, just take a paddle and make it as frictionless, slippery as possible, and you'll be able to beat your opponents because they won't be able to handle the spin the way it comes off a frictionless paddle when it comes back. All right. So what does acoustics and vibration? I'm an acoustics guy. I study sound and vibration. What does acoustics and vibration have to do with a sport? Like baseball, golf, tennis, hockey, or ping pong. My actual area of research right now is the acoustics and vibration of sports equipment. 20 years ago, I made a name for myself looking at the acoustics and vibration of baseball and softball bats. I've recently gotten involved with tennis and golf, done some work, supervised some students working with golf club drivers, working with putting right now and the interaction of the putter and the ball, some hockey sticks, and ping pong was a project we did recently that was kind of fun. So what's the relationship? Well, it turns out that in any sport that involves a handheld implement, like golf where you have a club, or baseball and softball where you have a baseball bat, field hockey where you've got a stick, ice hockey you've got a stick, cricket, tennis, racquetball, and even table tennis. Any of those games where you're hitting a ball with a handheld implement, the three things that matter the most to the person playing with that implement are the sound of the impact, the feel of vibration, and where it looks like the ball is going. And I'll just highlight that none of those three have anything to do with the actual performance of the bat, club, racket. It's just if it doesn't sound right and doesn't feel right, then players will not want to look to use it. So the photograph on the left here shows some research we did a few years ago with a golf club called the Sumo 2, the Nike Sumo 2. It was the best, highest performing golf club on the market at the time. So it hit balls straight down the fairway, long distances, very little hooker slice, but it sounded absolutely awful, and nobody wanted to play with it. Nobody wanted to buy it. It was a commercial failure because it didn't sound right. I've worked with some baseball and softball bat companies. If the bat doesn't sound right and doesn't feel right in the hands of a player, it doesn't matter how many home runs it hits. If it doesn't feel and sound right, nobody wants to play with it. Well, the same thing is true with ping pong, as simple as it might be. The sound that a ball makes with a paddle, not that you can hear that, I can't play very well, so the sound that the paddle and the ball makes upon impact does matter to players, especially to professional type players, in terms of the perception of quality of the instrument they're looking at. So a couple years ago, I saw some really interesting research by a group out of France that were looking at some ping pong paddles and trying to determine what the construction, the plywood construction, the laminate construction of the paddle, how that affected the perception of sound. And I thought they were doing some interesting things. They were looking at a laser Doppler vibrometer to try and look at some vibrational shapes and trying to get a correlation between the frequencies that they were hearing. And it looked interesting to me, but I wanted to know a lot more about the ping pong paddle. And I'm the kind of guy that when I've got a lab and toys to play with, if I've got an object that makes sound, I want to know how it works, how it vibrates. So I decided to take some ping pong paddles and balls into my lab and figure out exactly what is it about the racket, the paddle, that makes the sound when a ball hits it. What is it that makes that pop sound? But I also wanted to know about the ball. I hadn't found anything that actually explained what the ping pong ball contributes to the sound. So that's what I wanted to do. So I do this experiment called experimental modal analysis. I'm not sure if my mouse shows up on the screen here, but experimental modal analysis is a way of measuring the vibrational mode shapes and frequencies of a structure. So in this case, I had a really small accelerometer, a little transducer that measures acceleration. In this case, I had a small one that has a mass of about 0.5 gram, and I attached it to the handle of the ping pong paddle. And I have a small hammer here. The hammer has a special force transducer in the tip. So the tip of the hammer exerts a force when you tap the structure with it, and the transducer gives you a measurement of the force as a function of time, which you can then use a frequency analyzer to change that as how much force as a function of frequency are you imparting to the structure when you tap it. The accelerometer measures how much vibration results from that impact, and you do this on a whole bunch of points in the structure. So in this case, I made a bunch of marks on my ping pong paddle. So I did about 400, I think 300 points where I was impacting it with this little tiny hammer and measuring the response with the accelerometer. And then for each impact location, for a given accelerometer location, you get what's called a frequency response function. A graph that has, in this case, I was measuring the acceleration divided by the force. So how much acceleration results from an impact with a certain amount of force given to it. And the way that the shape of the graph looks here is as a function of frequency. The shape of the graph as a function of frequency, the peaks in this graph, frequency response function, each peak represents a particular vibrational mode shape of the structure. And these two graphs are different because they result, or they respond, or correspond to two different locations on the racket. So the top graph is hitting the racket at its dead center. The bottom graph is hitting the racket at an edge, and there are different vibrational modes that will show up at different points on the structure. So the experimental modal analysis measurement takes an impact at a hammer and an accelerometer location, and you take the ratio of acceleration divided by force, and you do this for all the points in the structure, and then all the points in the structure, and then you get a resulting map showing what the structure looks like. So let's see. Get my mouse back here. All right, so here's what some shapes look like. So a couple of vibrational mode shapes. Once, basically, you do this for all 300 points, and then I use a computer software program to curve fit the data so that you get a relative comparison of how every single point on the structure vibrates relative to every other point on the structure. And then you get these movies that I'm showing right now that show how the ping pong paddle vibrates. So There are some flexural bending modes. So the mode on the left here is a flexural bending where the whole racket flexes and bends. These are grossly exaggerated. They don't actually vibrate that much. This is magnified quite a few times just to show the effect, but you can actually feel the vibration. The thing vibrates, and the second pattern in the middle here shows a torsional twisting vibration where two parts are moving in opposite directions. There are a large number of bending vibrations. The bending vibrations are identified by the fact that if I look at a line down the central axis, the left and right sides or near and far sides are both moving up or down at the same time. So in this bottom picture, there's a node line down the middle of the racket, but there's a node line across the edge, but both the far and close edges and both the far and close edges are doing the same thing at the same time, as opposed to a torsional mode, a twisting modes, where the near and the far edges are doing opposite things. So it's more of a rotational twisting type of a motion. So all of those show up, and then there are some modes that I was really interested in. These are the ones where the center of the racket has a lot of vibration. And those could be important both in terms of the sound that the racket makes, as well as contributing to the power, like the performance. How well does the racket hit the ball? The more, if you hit the ball in the center of the racket with this picture on the right here, this, we'll call it a membrane type mode, that's where the ball actually gets thrown back from the racket, and the racket is powerful. And in the case of a tennis racket, that's the thing that actually allows you to have the power. How the strings, how tight the strings are, the tension of the strings is what determine how well the racket behaves. So you do all these maps. There are some bending modes, there are some torsional modes, there are some membrane-like modes, but the racket itself, the paddle itself, kind of looks like an elliptical plate with a handle. There's a handle on it, but there's basically an elliptical type plate. So I did some searching in the literature, and Ernst Chladni, and in the 1800s, he's the guy who sprinkled sand on vibrating plates and came up with all the pretty pictures of vibrating plates, circular plates, rectangular plates, triangular plates, and he did a bunch of measurements on all kinds of different shapes. And then a woman by the name of Mary Waller did some really impressive work photographing all the possible vibrations of a whole bunch of different types of plates of different shapes and geometries. And basically the ping pong paddle is very much like an elliptical plate. It just has a handle on it. So there are some modes that have a lot of wrong direction. There are some modes that have diameters, I call them diameters, or lines parallel to the minor axis. Some lines that have lines down the middle. There are some lines that have some kind of elliptical circular type patterns. So you can identify the different types of patterns. I guess this top row are kind of like a bending one. The middle, the second row would be like the torsional modes, and then there's some membrane type modes. So I just organized all my pictures. I turned them into some contour plots and organized them to try and look like this elliptical plate type behavior. I do have one pattern here that does not show up with an elliptical plate, because this is the flexural bending mode. This plate, this mode, if it was a plate, would not exist, because if the handle was gone, this would simply be a free body rotation, a rigid body rotation about a midpoint in the middle, right down the center right here. Because there is a handle on the paddle, then there's an extra node line. So the pink and the green, I've chosen these colors because I believe that they work pretty well for people who are red-blue colorblind. So the pink and the green are opposite direction amplitudes, and the white parts are the places where the structure is not moving. Those are the nodes. So the top row are kind of your, what we would call the bending modes. The second row are the torsional modes, and then we've got these kind of a membrane type things. The two that are going to be really important to the sound, or at least that some other people have identified as being important to the sound, and this is what I wanted to kind of explore in my research, are this, we'll call it the O2, the 0-2, kind of a membrane type mode. That's the one that has this strong amplitude of vibration at the very center of the paddle. And then this other pattern here, which is kind of like a bending vibration, which also has some strong amplitude of motion right at the center of the paddle. Those would be modes that contribute to both the sound and to the performance. All right, so trying to see how this looks like, I'm trying to relate this to the acoustics of the sound. I took a paddle and a ball and bounced it a whole bunch of times, about 20 or 30 times, and took a long average of the frequency spectrum just to get an idea of what frequencies show up in the sound when you're hitting a paddle and a ball. And so this is the resulting frequency spectrum. And There are shapes, so that really strong peak that's about 15 decibels, which is a huge difference in the sound level. 15 decibels above every other sound is this 0-2, let's call it a membrane mode, where the center of the paddle is very heavily engaged. It's very, very effective at radiating sound, so it seems to be the primary contributor to the sound. The second peak at about roughly 2,000 hertz. So I guess that first peak too, and this the peak. This is a paddle for which I have removed all of the rubber padding. So I'll show you what happens with the padding back on in a minute. So that sound we're hearing is composed of primarily the O2 mode at 1160 hertz and the 1-2, the other membrane mode, at about 1968. There is another higher membrane type mode at a much higher frequency, and then the two bending modes are much lower, but those are about 20 to 25 decibels lower than everything else, so they really don't contribute to the sound all that much. It looks like that 0-2 mode right here is the one that really does the sound that you hear when you hit a ball with a paddle. Well, most of us don't play with wood paddles, unless you're that physics professor who wants to try to beat everybody without having to worry about spin. We tend to play with paddles that have rubber padding on them, and the sound is a bit different. In fact, just to compare a couple things, I probably cannot do this very well, but let's see how good my skill is. So there's two, I'm using two paddles. There were two different sounds, going from with the wood to the one that has the rubber on it. Sound is a lot lower frequency because of the mass loading due to the rubber. So here's the spectrum, the frequency spectrum with the wood only, with all of the rubber removed, and then when I put the wood on it, everything drops. If I can go back and forth between these two, the frequency shift. There's one peak that doesn't shift. The first peak on the left, the one at about 190 hertz, doesn't change much, but all the other ones shift an incredible amount. So let me just try to maybe make this graphically. Here's the two. The top curve is the one with a wood paddle with no rubber. The bottom is the same paddle before I took the rubber off of it. And the bending modes don't change much at all because there's not a lot of rubber on the handle. So taking the rubber off really doesn't affect the modes that involve the bending and the flexing where the handle is engaged. But they do have a huge effect. The rubber mass loading from the rubber has a huge effect on the other modes. So the thickness of the rubber, the type of rubber, the weight of the rubber padding can have a huge difference on the quality of sound that a ping pong paddle makes. So if the really cheap ones you buy at Walmart or something may have a really thin layer of rubber coating, they're going to sound very differently than the much more expensive ones with a very thick layer of rubber coating, just because the rubber adds mass, which lowers the frequencies. The main reason that I did the experiment with the rubber off is that when you're using a hammer to hit something, the rubber makes it very difficult to get clean data. So hitting the hammer on a rigid surface, a much stiffer surface, was much easier to get nice clean mode shape data. In terms of the mass loading, the player's hands, when you have a paddle that's just suspended rubber bands and no hands, the hands actually drop the frequencies a bit because your hands add mass loading. The hands, even if you grip it tightly, don't completely clamp the vibration. They don't completely eliminate the vibration, they just reduce it, but the hands tend to primarily add a bit of damping but a lot of mass loading, at least for the two sets of vibrations that have flexural bending type modes. But the rubber padding on both surfaces of the paddle, those have a huge effect on the frequencies of the plate modes, the elliptical plate modes. So it has a big difference in the effect. All right, so I think that's about, a couple things about the sweet spot. So how do these, if we know that these are the frequencies that produce the sound, how do these vibrational mode shapes of the paddle have to do with the performance? So where is the sweet spot of a table tennis racket, of a ping pong paddle? Sweet spot in a baseball bat matters a lot, but where is the sweet spot for a ping pong paddle? And what it turns out is that there are two sweet spots. There's one for the feel. Here's a set of measurements. If you measure the acceleration on the axis of the, so down the middle axis of the paddle, and find out where along the paddle does it feel the best. The location on the paddle where it feels the best tends to line up almost exactly with the node lines, of the bending vibrations, and the torsional modes all have a line right down the middle, right down the center, but almost all of these first 4 bending vibrations have a node line very, very close to this one location, and it's kind of a general, it's got we call it a sweet spot, but it's more of a sweet region. It's got a bit of a width to it, about the size of, maybe about half the size of a ball. That's the region where if you hit it there, because you're hitting it at a node, the racket doesn't vibrate, the paddle doesn't vibrate, and so you don't feel a vibration in your hands while you're playing it, because it feels good, because you're hitting it at a spot that's not going to excite anything into vibration. It's not vibrating at that point, so none of those modes will show up if you hit it at the right location. Hitting at that right location, if they don't show up, they don't vibrate, that also means they're not going to contribute to the sound. But the position of maximum power, the maximum power spot, if you take a look at the rebound velocity, so you measure the rebound velocity as a function of location on the grip, that corresponds to almost the dead center of the racket, the paddle, where this membrane type mode has a large amplitude response, and that seems to suggest that that mode is the one, that vibrational mode is the one that contributes the most to the performance of the racket. So a way of designing this would be the frequency. We would really like, if this is going to be performing well, you want the frequency of this particular vibration, you want the period of the frequency of that vibration to be closely matched to the contact time between the ball and the paddle, if possible, to enhance the performance. That's why playing with on a tennis, you can change the stiffness of the strings, the tension in the strings, to get more power out of the racket, because you're affecting the dwell time of the ball in the racket to get it closer to the actual resonance frequency, natural frequency of the racket. Similar thing you could do with paddles. I don't know how well this is done yet. I haven't started working with any manufacturers yet to see about trying to design these. There is a playoff between, or a trade-off between, making it sound good and making it play well. So you could have something which plays really well, but players hate the sound of it, so that would be the drawback. But sweet spot is very much dictated by these vibrational modes of the racket. All right, what about the ping pong ball? How does the ball contribute to the acoustic sound of a ping pong interaction? Since 2000, the international regulations for ping pong balls, for table tennis balls, have been it has to have a diameter of 40 millimeters. The wall thickness is about 0.4 of a millimeter, and it has to have a mass of 27 grams. Prior to 2000, most of the balls were 38 millimeters in diameter, and I believe they went to 40 millimeters in diameter, made it a slightly larger ball, which made more air drag, which made it a little bit more difficult for high-performance players to be able to smash the ball quite so well. So it was an attempt to try and level the playing field at some of the international competitions. They felt that the best players were having too much of an advantage because of the smaller ball, so they went to a larger ball to try and slow the game down a little bit. Ping pong balls are made of cellulose nitrate. Here's a range of their elastic modulus, the Young's modulus, the density, and the Poisson ratio. Cellulose nitrate, I will make a comment, is extremely flammable, so if you want to do something really fun but dangerous, get a bucket full of ping pong balls and light it with on fire with a match, and it will burn amazingly. Just don't do it indoors. Don't do it anywhere near anything else that could catch on fire, because it is very dangerous. They are very, very flammable. But let's take a look at what the ball is. The ball is a spherical shell, a hollow spherical shell, and there is physics that determines the theory for the vibrations of spherical shells. So Horace Lamb did this back in the late 1800s. Baker did a little bit more accessible article that was a little bit easier to read than Lamb's original work. There are several modes of vibration. The lowest order mode of vibration would be what's called a breathing mode, where the entire ball expands and contracts like a breathing mode. These are almost never seen in a ping pong ball because it's extremely difficult to get the ball, the entire radius of the ball everywhere, to expand and contract. It's very, very difficult to do. The n=1 pattern is not really a vibration of the ball, it's just a translation back and forth, so it's really a rigid body motion that's really not that interesting. The n equals 2 modes are the ones where the ball starts squishing in different directions in different amounts, and those are the ones that would actually push air away to create a sound. So the theory, there's an upper, and there's also this upper branch thing, is a class of modes that only involve some tangential motion where the ball is vibrating, but not in a way that changes its radius. And in order for the ball to make any sound, it would have to change its radius. And the first class of modes only involve a tangential motion parallel to the surface of the shell, so they don't actually contribute any sound. The ones that do contribute sound are this lower class, a lower branch. N equals 1 doesn't do anything. N equals 2 is where it starts. And the N equals 2 mode, if you put in the values of the Young's modulus, you use the simple theory, by Lamb and Baker, and you put in the Young's modulus, the Poisson ratio, and the density, you get a fundamental frequency for the lowest acoustic mode of a ping pong ball at about 5,800 hertz. I like to do things multiple different ways, so in addition to just doing the math, I also made a COMSOL multiphysics model of a ping pong ball. It's a thin spherical shell with this type of material, relative the thickness and the diameter, the material properties, and you get a series of modes. The N equal 2 mode is the one I'm going to focus on because that's the one that seems to make the acoustic sound. The best effective radiator of these modes at about 5,800 hertz. There are a number of other modes, and these modes all follow a pattern. So the N equals 2, 3, 4, 5, and 6, they follow a pattern which matches the theory, the simple theory, really, really well. So it's just another way of computationally confirming what the basic theory says is true. This is something we did in when I taught undergraduate physics at Kettering. We developed an acoustics laboratory course that had a number of projects where we tried to get students into the habit of doing things as a theoretical, as simple as possible theoretical mathematical approach, do a computer model of the problem, and then use experimental data to try and back up and refine your computer model and your mathematical model, your simple physics model. So the physics and the computer model and the experimental data all kind of work really, really nicely. So I wanted to try and measure the vibrations of a ball. That turned out to be a little more challenging than I thought it was going to be. One of the first ways I did it was I suspended the ball on a couple of rubber bands underneath a very powerful high-intensity driver loudspeaker and just blasted sound through it, trying to make the ball vibrate very loudly. And then I measured put a microphone very close to the ball to try and measure any kind of radial displacement in the ball would push air and would make a resulting sound. And then if you divide the signal that was going to the loudspeaker and take the measured microphone response divided by the signal going to the loudspeaker, you get a relative difference between what the ball was being driven and what the vibration the ball was producing for sounds. And I did see significant peaks in the microphone response at a frequency of about 5,900 and a couple of other frequencies that matched what looked pretty close to the first, second, and third, the N equals 2, N equals 3, N equals 4 patterns for the ball as it vibrates. It wasn't enough for me. I wanted to do some other things, so I also took and measured something called the mechanical impedance. So this is a mechanical shaker, and attached to the mechanical shaker is a device called an impedance head that measures force and acceleration at the same point at the same time. So it's got two transducers inside this housing. One of them measures the force that's being exerted pushing on this object, in this case the ping pong ball. At the same time, it measures the acceleration at the point of contact. So and if you take the ratio of acceleration divided by force, or in my case, if you integrate the acceleration signal to get velocity, the ratio of velocity divided by force would be the mobility, or the inverse of impedance. And the system has resonances when the impedance becomes a minima, or when the mobility, the inverse of impedance, becomes a maximum. And I found an impedance minimum. That means that I'm driving the system with a force and getting a very big response, very big resulting vibration. I found an impedance minimum at 5,900 hertz, which is really close to what I expected it to see also. So the impedance measurement worked too. I did one more because I found an interesting paper by Rod Cross, an Australian physicist who does a lot of really fun things with bats and balls in the American Journal of Physics. And so I took the same setup and I dropped a very small ball bearing, so a 0.4 of a gram, 4.75 millimeter diameter, and just dropped the ball bearing on top of the ping pong ball and measured the resulting acceleration. So the accelerometer in the transducer underneath would measure the resulting acceleration of the system as I dropped the ball bearing on it. And I did in fact see a couple of peaks. One's a little bit lower at about 5,700 hertz, which if you take a look at the frequency of oscillation of the ping pong ball and mass load it, which lowers the frequency because of this ball bearing in contact with it, that came out to be right about the right number. So I did see the result showing what it looks like. And just to compare these results, so the theoretical value, the computational COMSOL multiphysics model, and the I did one more here that I didn't mention, just throwing the ball into a hard surface and just measuring the acoustic sound from the bounce as I throw a ball at a metal surface, a hard rigid surface. All the data, theory, and measured values come out to be very close to each other, at least close enough that I was pretty pleased that I knew exactly what the ball was doing in its vibration. I want to come back to this experiment for a minute, dropping the ball bearing on the ping pong ball, because I learned something else, and sometimes really simple physics can do some really interesting things for you. So in this signal, the 5,800 hertz is the natural frequency, the oscillation of the spherical shell. But there's this peak at 1,392 hertz that I wanted to know what was going on. And I suspected that maybe that was simply a mass spring problem where the ball bearing was dropping, the ball bearing acted as a mass, and the ping pong ball was squishing a little bit like a spring. So it's basically just a mass spring problem. There are many papers, I found several papers published that are using, there's a whole bunch of people that study, they use ping pong balls as spherical shells, looking at the way that objects squish and stretch. You take a whole array of spherical hollow spheres and try to look at how sturdy that is if you put a weight on top of it, and they measure the compression rates and the deformation and the buckling of spherical structures. Ping pong balls are really convenient, they're cheap, you can buy a whole bunch of them and put them in a lab and test them. And so if you simply take a ping pong ball and squish it, you get a mass spring curve. Same kind of thing we do in a freshman physics lab where you hang a mass from a spring and you measure Hooke's law. So if you plot the deformation, the amount of squish versus the force, you get a straight line. And if you take the mass of the ball bearing, and if I extract the effective stiffness, the effective spring constant of the ping pong ball getting squished from the published data of the deformation versus force curves, I get 1,390 hertz. Dead on. It was really cool. So basically, it was just the ball bearing was a mass, and the ping pong ball was acting like a little spring, and I was able to explain what that peak was. So kind of a really cool, simple physics problem to explain a piece of data. All right, that's what it is. Okay, now here's a really good, interesting question. If I go back to looking at what the sound looks like from hitting a ball on a paddle, and say, if that's the sound that it makes, and I look at the spectrum carefully, I notice that there is absolutely nothing showing up at the 5,800, 5,900 hertz location where the ball should be contributing to the sound. In other words, it appears as if the ball, even though it has some very prominent, measurable vibrations, structural vibrations that should and do radiate sound, the impact between the ball and the paddle, there's nothing showing up. So it doesn't look like the ball is actually contributing to the ping pong sound at all, and I wanted to know why. So I did a little bit more digging. Well, I tried some experimental stuff too. So I took a ball, found this really, really massive steel. It's rusted, so that's kind of an orange color. This big, massive piece of steel, hard, heavy, flat surface. I embedded in some sand so it was really, really stiff, not going anywhere, and I took and dropped the ball, or threw it as hard as I could, onto the surface and simply measured the impact sound, trying to make sure that I was really able to see the sound of the ball as a result of an impact. And you do see, this is the measured microphone response, there is a small peak here at about 5,900 hertz, which is exactly where it should be if that fundamental oscillation of the ball is producing sound. And I'll come back to this in a moment. There's a whole bunch of stuff around 8,000, 9,000, 11,000, a whole bunch of high frequency information that showed up way higher. So I know that when I throw the ball at a steel rigid surface, the ball does oscillate with 5,900 hertz, seeming that it should contribute a sound which should be detectable when I hit it with the paddle, and yet when I make the measurements hitting the ball with a paddle, I get nothing at that frequency. So what's going on? Well, I found this really cool study by a molecular physicist by the name of Daniel Murray. He passed away a few years ago, but he's got a couple of websites that his university thankfully kept up, because this is some unpublished research that I found, that he was doing some modeling of spherical shells, and he modeled a ping pong ball, not by doing the math and the structural acoustics like I would have expected to do, but he modeled the ping pong ball by looking at the molecular dynamics. He modeled the ping pong ball as a collection of molecules and just looked at the way that those atoms and the molecules interact with each other, and he basically let the ping pong ball drop and used his simple physics, he used the physics of molecular dynamics and molecular interactions to simply predict what would happen when a ball drops and hits the surface. And what he described in this online paper is that the period of the fundamental, this 5,900 hertz signal, has a period of about roughly 0.2 of a millisecond. But the contact time, the time of contact between the ball and a hard surface, is about 3 times that, 3 to 4 times longer. Or if the ball is impacting a soft rubber surface, it can be almost 10 times, 8 to 10 times longer. Which means that the ball, those acoustic modes of the ball, even though the ball wants to oscillate and wants to radiate sound, the acoustic modes of the ball are suppressed because the contact time is just too long. All right. And there's a lot of other research too, which I looked up and found. And there's a whole bunch of people that have done some high-speed video of balls being shot out of cannons at like 40 meters a second, hitting a surface. So this is the picture that shows some side views, and they shot it at plexiglass. You can see the upside view, and there's actually some buckling. In this case, it was interesting. I was looking at this first of all just to get a sense of exactly what is the contact time between the ball and the paddle. But then when I started looking at this research where people were looking at this, I noticed that the ball, when it contacts the surface, so these pictures on the right are still frames of a movie showing the ball impacting a plexiglass clear surface, and you can see that the ball buckles on the inside. The same thing happens with a basketball. The reason a basketball makes a thump sound when you bounce it off the floor is because the bottom of the basketball is actually buckling in and then popping back out. Again, there's a really interesting paper in the European Journal of Physics that describes the thump of the basketball in terms of this popping sound. If you take a basketball and slap on the basketball, you're hearing some spherical standing waves. And I wrote a paper in the American Journal of Physics about the basketballs as a spherical acoustic cavity that explains the ping sound when you hit a basketball. But a ping pong ball, it's called a buckle and a snap through on the surface. Well, I don't know if this is going to work on the recording. I will try. But if you take take a ball and hold it to a microphone, and this one is not real good. It's not popping. Let's try the other one. This ball might be too soft. No. If you get these balls, I think we're sitting out and they've gotten moist, so they're not snapping. If you take a really fresh ball and put it with your finger, you can actually see it deform, and then when you let go, it will snap back. And this is a recording of the snap pop, the popping and the snap through afterwards. And notice that there's a huge amount of frequency content between about 9,000, 10,000, 11,000 hertz, which is right what I was seeing when I was throwing the ball against that rigid surface. So here's what I've learned about the acoustics of ping pong. The sound that you hear when you bounce a ball, tap the ball with a racket, whether it's got rubbing padding on it or not, tends to be dominated by this primarily membrane type mode in the racket, where the center of the racket has a large amount of vibration. That's what largely contributes to the sound. So designing the racket in such a way that that particular mode shape has a certain frequency would be important to a manufacturer trying to make their racket more palatable or popular with players who are listening for a certain type of a sound. The ball does have a very easily measurable acoustic mode that should radiate sound, except because the contact time between the ball and the paddle is about 4 to 8 times longer than the period of oscillation of the ball itself, those modes get suppressed. But there's some high frequency, especially when you slam the ball or when the ball hits the tabletop and bounces off. There are high frequency modes of our high frequency sound that comes from the snap and the pop through that results from popping. That one's working a little better. There we go. That high frequency snap. That high frequency snap is the result of popping through when the ball hits the surface. So, if you're interested in more details, I published a paper on this, and there was a special issue on table tennis in the Journal of Sports Sciences that I was able to publish a paper in that does this. But that's an introduction or a summary of the acoustics of ping pong paddles and ping pong balls. And I see that there are some questions. So I don't know, Kayla, if you wanted to pull up the questions, or I can see if I can try to find what they are too.
I have them pulled up here if you want me to read them off for you.
Sure, go ahead.
So the first question was, how do you know what sounds good for players on different sports equipment? Did players give perception evaluations?
That is a great question, and that's the $64 million question. Trying to find out exactly what it is about a racket or a ball or a club that people prefer. That's what the manufacturers are spending their money on right now. So golf club manufacturers are doing a lot of research right now trying to figure out what is the preferred sound of a golf club driver, or what baseball manufacturers are doing a lot of work. In fact, I see Linda Hunt has got the next question. She's one of my former students working out at Easton. Trying to design a baseball bat to have the right sound is a critical thing because a player wants it. So the question of what is the magic, the perfect sound, that's the one thing that we're trying to figure out. I've got a project going on with some golf balls and putting. In the game of golf, the driver gets all the attention, but in the putting game, the sound that the ball makes is critical to a player's perception of how good a putt they just made. So trying to tune a ball or trying to tune the putter to make a sound is critical, but I don't know the answer because it's very, very player dependent, but that's what a lot of people are trying to spend their time trying to figure out what the magic sound is. I think the second question, you've got it pulled up. I did get it pulled up here, Michaela. The second question is, why are the 2O and the O2 modes the important ones to player perception? I think the reason those are the ones that are important to player perception is simply because they're the ones that contribute to the sound. So the 2O mode is the bending vibration that would have a sense in where the feel is. So that would the 2-0 mode on the racket would determine what a player feels is like, where the sweet spot for feel is, where on the racket's the feel, and the frequency of vibration and the shape of that would be what determines the sweet spot. The O2 mode is the one with the membrane, and that's going to determine like the maximum power spot. I don't know, I haven't done enough research yet to know exactly how important that is in terms of, does it make a difference of, how many meters a second does the ball come off? That's something I don't know. I don't know the answer to how much of a performance issue it would be. I know in baseball and softball bats we have to worry about something called the trampoline effect, and so you actually have to design the barrel of the bat to act like a spring to try and increase the performance. So I'm not sure about that. I noticed that a question related to this just came up on the chat window. Randy Warland was asking, does the firmness of a player's grip make a difference in the sound or performance? And the answer is no. This is one thing that's surprising in almost all sports. The purpose of your hand grip is to get the racket or the paddle where it's supposed to go. But the collision is too short, and even in ping pong, the amount of forces between the ball and the paddle are enough that the hands are not doing anything. The hands are not damping the vibration, clamping the vibration enough. The vibration still exists even when you grab it. So the hands do lower the frequency a little bit, and it does damp things so that the frequencies die away faster, but it doesn't really change. It's the material properties of the handle that have the biggest effect. Let's see, another question. I may have missed this, or it could be coming up, but did you measure the acoustic output of the ball and a paddle with the rubber removed to see if the contact time is shorter? So the data that I showed where it was missing was the data with the rubber removed, so it was as short as possible. So it was actually the data that I showed for the sound spectrum with the 5,000 hertz missing was actually bouncing it off of a wood paddle, which was as hard as possible. And even on a hard surface, the contact time is still at least 4 times the duration of the period of the oscillation, so it just doesn't, the ball is trying to vibrate, but it's still in contact with the racket during that time period. Let's see. How do we know the drops in the frequencies in the case of rubber pads is because they added mass and not the damping? Because the mass loading has a huge effect. So the damping does lower the frequency a small amount, but not nearly to the extent that the mass. In this talk, I did not include the amount of mass, and I don't remember off the top of my head. I'm not sure if I've got it in my lab notebook here or not. The amount of mass, the fraction of the mass of the rubber padding was actually surprisingly large, like 25% of the weight of the racket. I don't have a plot here. So the both layers of padding, there is between these two rackets that I'm holding in my hands. One is they're identical rackets. One has padding and one doesn't. It is at least a factor of 2 in the mass difference between the one that has the padding and the one that has no padding, the rubber padding. So the rubber padding the mass loading is extreme, and it's going to have a lot more. The mass loading is extremely high, and it would have a much greater effect than the damping. Tuning the O2 mode, so have the paddle to the first mode of the ball have an increase in power. That's a question that I want to play around with in the future. I don't know the answer. I believe what would be more likely is to tune the O2 mode so that its period matches the contact time of duration of the ball. So, 2 milliseconds. Can't do that math in my head on a Wednesday afternoon. Grab my calculator. 2 milliseconds. So 0.0002, 0.2 of a millisecond. Flip that upside down. It's about 5,000 hertz. No, yeah. So if I want 4 times that, so about 4 to 5 milliseconds, so 0.005. So you would need to have that frequency of the 0-2 mode be around 2,000 hertz in order to maximize the vibration of that O2 mode with the contact time of the ball. And that's what seems to work really well in baseball bats. You do it with a baseball bat, you basically make the bat illegal because it can't be used for play anymore. You do it in golf clubs. The trampoline effect in a golf club is tuned so that the frequency of oscillation of the front face of a driver is about roughly the same as the contact time. Tennis rackets is a similar thing. So if you could do this with a ping pong pad, if you could tune it, it would be a higher frequency. So 2,000 hertz is definitely a lot higher than the frequencies of current ping pong paddles. So the question there would be, if you could tune it to make it more powerful, would that change the perception of quality in the hands of the player? Would the players dislike a higher frequency sounding paddle, or would they, like it better? And I don't know the answer to that because I haven't seen enough data with enough tests from players.
Dan, I think we're going to have to cut it short there.
All right.
We have gone over a little bit, but
sorry.
No, it's not a problem at all. I'm glad there's so many good questions. I just want to thank everybody else for joining us, and I just want to thank specifically you, Dr. Russell, for joining us and taking time out of your schedule again.
My pleasure.
This was awesome, and we will be posting this talk on our YouTube channel, so if anybody wants to share it, feel free to do so. And we will see you all at our next talk. Thank you, guys.
Great.
Have a great day.